So I'll leave it to him. Take it away.
Thank you so much. Can you all hear me all right?
Yes, sir.
All right, pretty good. So I have been doing a presentation, and as you said, did this one a couple months ago on sort of Georgia Energy Code. Southface went out and did a big energy code field study, gathered some data, looked at areas of low compliance, and sort of doing a presentation about what we found and what we really want people to be looking at in new homes. Quick show of hands, who was there in Tucker for that presentation? Okay, about half maybe. We'd be happy to do that, but actually Will and I talked a little bit, and he said, you know, there's been some questions about load calculations, ventilation, spray foamed houses, and could you talk about that? I said, sure. And in fact, this is a topic that we get asked to talk about pretty frequently. The presentation that I'm going to show today is a version of a presentation that we did about 2 years ago in Alabama for a home builders conference. And, you know, we've probably been teaching this sort of concept for, I don't know, 10 or 15 years. And so it's something that comes up over and over and over again, and people have questions about. So I can tell you what the energy code and the building code say about ventilation and about load calculations. And I can do that on one slide, and then we could all go home. Good. Because it's really not very complicated. I'll show you that in a minute. But rather than putting up one slide and saying, look, the codes say you're supposed to do this stuff, and here's what they say about it, I thought it'd be a little more interesting to give y'all kind of some real-world examples of how load calculations are affected by what you're doing in the home, and how that sort of ties in with requirements for ventilation. And then also be in a real-world scenario, something we see a lot is what happens when someone spray foams a roof line or an entire house, and what are the implications there. And that's a common retrofit we see. In fact, I just taught a workshop on Wednesday for the City of Atlanta code officials, and there was a lady there who was a plans reviewer, and she was in the process of having her house roof line spray foamed. And we basically went through the same type of stuff I'm going to talk with y'all about today, which is, okay, you're changing the thermal envelope. That means you've got a different system that your house is operating under, and that's going to have some different considerations for how you heat the house, you know, what type of furnace you put in there, ventilation you have to bring into the home, and they were replacing their duct system, moving it from a crawl space into that foamed attic, and talking about, you know, you really need to do a load calculation, right? Because you've changed how the house works, and you're moving the system from a crawl space into an attic, but you're putting it into a sealed attic rather than a vented attic. So this is something that we see all the time in the real world. It's a common retrofit to do this in an existing home, and then it's also, as I'll talk about, stuff that we're starting to see coming into the energy code and the residential building code, the IRC. We are moving to a future where houses have to be tight and where houses have to have ventilation, mechanical ventilation, not uncontrolled air changes. And so I think that we used to look at a spray foam house and say, well, that's an unusually tight home, so we got to think about combustion safety and ventilation air and all this type of stuff. The energy code and the building code has pushed us to a point where all new homes are tight homes. And all new homes are going to have to think about ventilation and combustion safety. So I think this is a very good topic for kind of where we are in the construction industry right now. The building code, Ted was here yesterday. Did y'all get a chance to see Ted from DCA?
Yes.
He talked about Georgia Energy Code updates. Right now we're going through a process in the state. We're reviewing what's going to be the state's next energy codes based on the 2015 IECC. Mike and I are involved in those conversations. Quick show of hands. How many of y'all know Mike Barcer from Southface? All right, in this crowd, I am more famous than he is now. That's great. Because usually it's the other way around. Everyone knows Mike. But he's been at Southface about 20 years, co-worker of mine, does a lot of energy code stuff. He's on the state task force, and then I'm working with him as well. So we're going through that process with the state, and it looks like the next version of the state energy code is going to be something based on the 2015 IECC. It's going to require more insulation, better lighting, tighter houses, tighter duct systems, and ventilation. And we're really working hard to get out of this place we're in now, where Houses are required to do a blower door test, and they're required to be 7 ACH 50 or tighter. But if you're 5 ACH 50 or tighter, you get the ventilation penalty out of the IRC. And that's kind of a bad message. So we're hoping that this next version of the code, if adopted as written, will say that all houses require mechanical ventilation and all houses are supposed to be 5 ACH 50 or tighter. So I think in the future, we're going to see that all of this stuff, proper load calculations, proper ventilation strategies, it's all going to have to be done in new homes, regardless of whether or not they're spray foam houses. I also think we're going to continue to see a lot of spray foam renovations because it really does work if you do it correctly. Like a lot of things, you can do a bad job or a good job. If you do a good job, it works pretty well. If you do a bad job, yeah, you can create all types of problems. All right, so I promised this. Oh, here's what we're going to talk about. Energy efficiency, energy usage in homes, what affects your load calculations, what do we do, what's different in a foam house, and then considerations, really, it says foam houses, but it ought to be tight houses. And ventilation, fire code, combustion safety, and then a couple things about how we can do trade-offs of the prescriptive code, and also how we can test some of these homes. So I said I could teach you what's in the code around ventilation and combustion or load calculations pretty much in one slide. And this is that one slide. The current state energy code is the 2009 IECC with state amendments that were put in place in 2011. Georgia's been on that code for 6 years now. There are energy requirements in the IECC, including a requirement to do a load calculation and to size the HVAC system to that load calculation. Now I'm going to tell you how to do a load calculation. Requires a piece of software, requires somebody who is either an HVAC tech or an engineer that knows how to do the software. We could teach a class on that, but it would take a couple days. So in general, I think what y'all need to know is that load calculations are required and that you're supposed to size to them. Like anything else, junk in, junk out. If someone does it right, they follow the rules, they come up with a legitimate load calculation. If they want to fudge the numbers and they want to justify the system they've already decided to put in, this house needs a 5-ton system, and that's what I want to put in. They can mess with the load calculation, adjust the outside temperatures in the winter, adjust the outside temperatures in the summer, tweak the infiltration rate, change things around that go into the load calculation, and produce an answer that matches what they've predetermined. And the only way to catch someone doing that, honestly, is to get their file and go through all of their inputs into the file to make sure they follow the rules. So that gets a bit more complicated. Guys, I'll come right back over here in a second.
Yeah.
This also ties you into the IRC, where it says if you do a blower door test, and if you have a tight house, and that says 5 ACH 50 or less in this version of the IRC the state of Georgia is currently on, the 2012 IRC, then you're required to do ventilation. So under our current energy code, you're required to do a proper load calculation, you're required to size the house to that load calculation, you're required to do a blower door test, you're required to be 7 ACH 50 or less, and if you test 5 ACH 50 or less, the IRC is going to require you to put mechanical ventilation in homes. That's where we are in Georgia right now, and we're going to be there until the beginning of next year, when we're going to update to a new code, and when I'm hoping that it's going to be based on the 2015 IECC, and that it's going to require mechanical ventilation in all homes, and still require proper load calculations. And the reason we want to get ventilation in all homes is it's a really bad spot to be in right now, where you have to blow a door test and you have to be less than 7, but if you're tighter than 5, you get penalized by having to add ventilation. We'd rather have everybody know they need to do ventilation up front, design and plan for it, rather than finding out at the end when it's going to be complex and expensive and may not even work particularly well. So that's kind of where we are now and a little bit of where we're going in the future. I have 2 questions over here. Start right there.
The requirement for load calculations, that applies to an existing home as well?
It would apply to an existing home when mechanical systems are replaced.
Okay.
Yes, and I'll tell you, it's probably one of the least enforced things in the code. If you have a 5-ton system, they can come out and swap it for another 5-ton system. Nobody ever does a load calculation. But the load calculation is a function of a whole lot of other things going on in that house, as we'll talk about. And really, if they're going to replace equipment, they ought to assess the existing home and determine the tonnage that it needs and not just do a one-for-one swap. That's particularly true when they've done a spray foam roof line renovation.
You're gonna love this. Last month, my son-in-law called me up and says, look, I get the price on replacing my upstairs AC unit, and one contractor's recommending a 2.5 ton, the other contractor's recommending a 3 ton. What should I do? That's what I have the guy that you make more of his quote from Manuel J and tell you what the answer is. So he goes back to the guy that actually had given him the best price. And I asked him to do that, and the guy says, and I quote, well, I don't really mind doing it, but I can make it turn out any way you want to.
Yes.
So do you want me to waste the time? Because I'm still going to recommend a 3 ton unit.
Yeah. And that approach is not based on building science. It really isn't, right? Because he is taking a rule of thumb and yeah, I think that this looks about right for the space that you want to serve, rather than assessing what's actually going on in the home. Now, again, if nothing else has changed, if you're doing a one-for-one exchange, there might not be a problem, but in particular, when other parts of the home are being renovated, when an addition's being done, when we're spray foaming a roof line, things like that, they really need to factor in the conditions of the home as it is going to be operating with the new system, or they can't right-size. And the big problems, with not right-sizing are primarily, one, you're paying for too much equipment up front, right? Because you pay by the ton. And so if you oversize the equipment, you pay more first cost. You get basically shortened lifespan on the equipment because it's going to cut on, cut off, cut on, cut off, because it reaches set point very fast because it's oversized for the space that it's serving. And residential HVAC systems primarily do one thing, make cold air and reach set point as fast as possible. So when they short cycle, because they're oversized, you get stop, start, which isn't good for equipment lifespan. And then they never reach steady state operating conditions, and so they don't effectively dehumidify. So you get comfort complaints, you get moisture problems, you get more upfront cost, and you get shortened equipment lifespan. But what you don't get is contractor callbacks because the thermostat can't hit 70 on the hottest day of the year. Right? So the motivation is, if I would sell HVAC, hey man, I can make a ton of cold air and I want to sell you a lot of capacity because I'm basing my price on the tonnage that you're paying for. So of course I want to sell you a big system.
It's by going with the higher unit because he already increased his ceiling installation from R30 to 48.
Yeah. Yeah, so again, you got to assess what are the conditions of the home and what are the loads based on those conditions. And if you don't do that, then you're guessing. Maybe it's a good guess, maybe it's a bad guess, but either way you're guessing. Question? Comment?
We had a legal talk before this and going to another energy conference, and I've heard the contractors, liability entails now, they're required by the code to do load count. So if they missize the system and the 4-letter word in our business, MOLD or some other issue arises, particularly a health issue, they're liable.
Yeah, I mean, this is a state-adopted code. They are liable to build to it. Contractors are supposed to comply with the state-adopted codes regardless of local jurisdiction enforcement, which is another interesting thing we see. Jurisdictional enforcement is not consistent across the state. Some jurisdictions do really thorough jobs. Some jurisdictions do next to nothing around this code. Builders are obligated to build to the statewide adopted code regardless, and that includes proper load counts. And on the residential side, it not only says do a load count, it says you have to size to it. In the commercial world, it says the engineer has to do a load calculation, but then they get basically the choice to ignore it or pay attention to it. That's in the commercial world. In the residential world, it's clear. Do a load count, size the load count. So that's the law. Now, I don't know if people are getting sued for bad load calculations. Probably not a rampant issue, but it is the law.
Well, if you get mold as a result of an improperly designed system, then
Yeah, for sure.
lawyers like that.
Lawyers like that. Let's keep lawyers in business. Oh wait, let's not do that. Okay, so the last thing on this is we have this thing called an energy certificate, which is supposed to go in a new home and tells you all this type of stuff about the house. And it tells you the R values they put in, it tells you what they got on their blower door test, it tells you what they got on their duct pressure test, and it has a summary of the mechanical system that's installed. So you can't tell how they did the load calc, but you can look on this certificate, and you can look at the model nameplate on the air handler and the outside coil, and you can know whether or not at least what they reported on the certificate is what's actually installed in the home. Now, if I'm a really thorough code official, I'm getting the mechanical contractor to provide me with a summary sheet from their load calculation, and then I'm going to take that and I'm going to compare that to what's on the certificate, and I'm going to compare that to what's installed in the house. All the information is there if you wanted to do it. I'm going to tell you that's probably one of the most commonly ignored requirements of our energy code, because it's a mystery to a lot of people. And so I think code officials, code inspectors that are out there, a lot of times they're not catching people either doing bad documentation or, quite frankly, not doing any documentation at all on HVAC load calculations.
I have a user license, and I'm approved by the state heat management. I call this out all the time. You look at those numbers on there, your latent system load, look what they got. I'll make a note, according to your calculations, you got the wrong size system. They'll go back 3 or 4 times and change those numbers. They don't have a clue what those numbers mean. They just put them on that sheet paper.
Exactly right. And it is probably one of the least enforced and most important requirements of our energy code. And it's what you just described. Even folks in the heat and air industry are like, you know, I come out, I look at the square footage, so many square foot per ton, you know, 1 ton for every 400 or every 500 square feet, basically. I know the square footage, I know the size system that I need, that's what I put in the house. It has nothing to do with the fact that over the last 20 years, our houses have gotten better insulated, they've been starting to build out of sheet goods, they've been air sealed, you know, and they've got better lighting, all different types of things that mean lower loads on those houses. High performance windows, a big factor that means, you know, the rules of thumb from 20, 25 years ago are not applicable to new homes constructed today.
But the problem is builders are still buying here by the ton. So the heat air contractor, he puts some correct size system like this, and so we get to put something in too large, because that 3-ton system only costs $7 more than the ton and a half system, but he gets $2,000 more.
We really ought to not pay by the ton. It doesn't make any sense, and that's what we were talking about. You're incentivized, right? If you're the HVAC contractor, more tonnage the better, because 2 things. The system's always going to make cold air fast. That feels good, right? Feels like callback prevention. And you're selling, your price is based on tons installed. So 5-ton system is better than a 3-ton system, even if the house needs a 3-ton system, because it always makes cold air fast, and you sold more equipment up front, and that's what your price is based on. So there is an incentive, if you're in that industry, to oversize. All right. So, you know, Southface, what we do is largely around energy efficiency in the built environment. We're a nonprofit. We've been around in Atlanta since 1978. And we really are interested in energy efficiency in houses and in commercial buildings. This is looking at energy used in homes. We've got some statistics from '93, some statistics from 2009. I don't have a 2016 or 2017 update, but hopefully I can get one that's a little more recent in the coming years. This information comes out from the Energy Information Administration, EIA. They provide this data, so hopefully they'll get us some new data soon. But if we look at 1993 homes and where they're using energy, space heating used a little more than half of the energy in our homes back in 1993. Air conditioning, a little less than 5%. Water heating, in the ballpark of 20%. Appliances, electronics and lighting, in the ballpark of 25%. For a total energy consumption for your average home of basically 10, and I think this is million BTUs, quadrillion BTUs? Quadrillion BTUs. What is a quadrillion? It's a lot. Billion, quadrillion. I'm hoping when I get done this afternoon, I go check my bank account. That's all it says. Quadrillion! Sounds good. It's a lot. And then we look at 2009. And you see that the pie has actually gotten larger, right? All this energy efficiency stuff that we've done, and the energy used by the average house is actually slightly more today than it was in 1993. And so you look at that and you're like, well, what's going on? And you see that we've shrunk the piece of the pie for heating significantly. We've increased slightly the piece of the pie for air conditioning. I think this is quite frankly because more homes are air conditioned today than were air conditioned in 1993. We've shrunk the pie a little bit for water heating. We grew by 10% the piece of the pie that is basically plug loads. This is a reflection of the fact that we plug way more stuff in our houses today than we did, 20 years ago. Who has 2 refrigerators in their house right now? Yeah, right? How many people, 1985 had 2 refrigerators in the house? Right? How many people have more than 3 televisions? Exactly. How many of those televisions have a DVR system of some sort on them? At least one, if not all of them, right? So how many people go home and plug in a laptop and a tablet and a phone, right? So we're plugging way more stuff in than we used to, and lo and behold, it shows up. We've trimmed all these other things out. Whoops. We've trimmed down all these other usages, and we've given it all back with plug loads. So just an interesting problem that we kind of have. Plug loads are not regulated by the energy code, right? So it's good. We've weaned out all these other things because technology was going to have us plugging all this other stuff in anyway. But we gave back all that efficiency in plug loads. So the new frontier is managing plug loads. And we're even starting to see this in the commercial energy code where they're more rapidly integrating new technologies. They're going after plug loads. They're going after wall plugs that turn off automatically. They're going after automatic lighting controls because you reach diminishing returns. You can't do much more in our climate zone by just putting more insulation in the building. And you can see the piece of the pie is growing for plug loads, and so they're starting to go after that in the commercial energy code.
Yeah, I was going to say that 2009, so don't you think 2016, 2017 with the LEDs, CFLs, is there a pretty dramatic change?
I think so. I think that the 2 things that are improving are lighting and appliances. Those are getting better and better and better basically because of regulations. I don't think that we're going to be better in 2016 or 17 for plug loads than we were in 2009. I think we're going to be worse. I think more stuff is plugged in now than was plugged in 2009. So when this data comes out, it'll be interesting to see how that slice of the pie adjusts because lighting and appliances have gotten better, but I suspect that plug loads have gotten worse.
What does that number in the middle represent again?
This is energy consumption in homes, and I think what they're saying is this is total of quadrillion BTUs by percentage. So all the homes in the U.S. used 10.01 quadrillion BTUs in 93, and all the homes in 2009 used 10.18 quadrillion BTUs, which is energy input. And so, what in our homes that is regulated by our current codes is driving the use of the HVAC systems? Because even though I just harped a whole lot on how this number has grown and it's a big number, you still look at heating and space cooling, and you're talking nearly 50% of all the energy used in a home, right? So heating and space heating and space cooling are still a big deal. Even though the slice of the pie is growing over here, they still matter the most in terms of what's driving energy usage in our homes. And if we come and look at, what's driving our demand for heating and cooling in our homes, turns out that infiltration, leakage on the home's envelope, duct leakage, and duct losses and gains, basically conduction through the insulation of the duct system, are responsible for about half of that demand for heating or cooling. So they still use about 50% of the energy, and then these big areas, home infiltration, duct leakage, and duct loss and gains, are about half of what's driving all of that demand. So these things still matter. These things are still big opportunities to reduce our energy use and make our homes perform better. And in order to kind of get there, we use this concept of the house as a system. And this is really a fundamental of building science, which says the home needs a complete building thermal envelope, which means continuous insulation and continuous air barrier. The two need to be physically touching and complete, separating conditioned space from unconditioned spaces, whether it's outside, attics, crawl spaces, or basements. Properly sized heating and cooling systems, that means you match the equipment that goes into the house to the actual load on the house rather than by general rules of thumb. Controlled ventilation, we're making tight homes. We want to eliminate uncontrolled air changes, and for human comfort and for good indoor air quality, we want to give back a little bit of those air changes, but we want it to be done in a controlled way. Quick show of hands, who likes breathing crawl space air? Oh yeah, you've been in too many crawl spaces. Who likes breathing attic air? Nobody, right? If I have uncontrolled air changes in my home, maybe I'm lucky and they're coming from the fresh air outside, but in all likelihood, they're probably coming from my attic, from my crawl space, from my basement, from places that I don't actually want to breathe the air. So what we're trying to do from a building science standpoint is eliminate uncontrolled leakage by creating a perfectly airtight and insulated thermal boundary. Then we're trying to reintroduce controlled ventilation so we get to know how much, where it comes from, and when we ventilate that home. That gives us the best of both worlds. Adequate ventilation for indoor air quality and human comfort, control of air changes for energy efficiency and for good IAQ, and a home that actually works well. It's comfortable inside, has good indoor air quality, and provides the fresh air ventilation that we need for human occupants. And then, because we live in a sea of humidity, let us not forget we have to deal with moisture. It's a big deal here in the Southeast. And it goes back to the idea of short cycling. You know, we rely basically on HVAC equipment to run for a long time, to move a lot of warm, humid air over the coil, and to wring moisture out of that warm, humid air to dehumidify. If you have short run times, it takes about 15 minutes of run time for that interior coil to reach the operating state where it starts to effectively dehumidify. If you get 7 to 10 minutes of runtime every time your HVAC comes on, and then it kicks back off, you never actually dehumidify. You really don't effectively dehumidify the air in the home because that coil never really gets cold enough to start wringing moisture out of the air. So we've got to deal with moisture load in our homes here, and tightening up the house can actually help. People worry that when you tighten up the house, you're going to create mold issues. You could if you tighten up the house and you don't reintroduce fresh air ventilation. That would be a bad thing. But if you tighten up the house correctly, you size the equipment correctly, and you properly introduce fresh air ventilation, then you're set up for success in managing potential moisture problems in the house. All right. Real quick sort of review of building science, because when I say the house as a system is a building science-based approach, this is what Southface's world is based on. These concepts of how do houses deal with the transfer of heat, air, and moisture, and what is the science behind it. So we say you gotta have a complete continuous thermal boundary, an insulation and air barrier. We're looking at an infrared image here of an attic. It's cold, we're up in the attic, it's ventilated, it's winter. I can see the house is heated, and I can see all of this heat loss. Could be because of air leakage, could also be because this bat is not in contact with its air barrier. Got a piece of drywall, chipboard, trying to keep it 70 on one side. It's 40 degrees, outside air temperature on the vented attic on the other. Conducts through that little piece of chipboard. That surface gets warm, and then it starts to radiate heat because this bat product is not an air barrier, and it doesn't provide resistance to conduction unless it is in contact with an air barrier. So when it's sitting like this, and it's not in contact with that sheet good below it, it really has almost no effective R value, very little effective resistance to conduction. This is a common issue we see in homes where ceilings are penetrated with can lights, they're penetrated with wiring drops, all types of things. They've got air leak pathways, and then they've got poor insulation installed on top of them that's not even in contact with the air barrier, and they're huge thermal bypasses. And you've got a space up there, yeah, it could be 40 degrees in the winter, and you're trying to keep it maybe 70 inside, that's a 30-degree delta T, but it could be 120 degrees in the summer, You're trying to keep it 70 inside, that's a 50-degree delta T. That's why we put so much attic insulation in anyway. Big delta T, big temperature difference. So this is a high-stakes area for our thermal envelope, and it's almost always done poorly when people go in and try and put in bad insulation against a ceiling. It can be done right, it's just hard to do correctly. And then you take the same picture and flip it over, what is it now? It's crawl space. You're looking up at a floor. Same problem, right? Been in a crawl space and the bats are sagging down. They actually have no resistance to conduction unless they're installed in contact with that subfloor. And then you got to compress them to keep them in place with the subfloor. A hung bat trying to stay up against a subfloor in a crawl space or a basement is fighting gravity. You know, it's not going to stay there very effectively, and if it comes out of contact with that subfloor, then again, it doesn't perform. So these are two big areas where we see traditional installations struggle. Heat flows in three forms: conduction, convection, and radiation. It always flows downhill from more to less, from hot to cold. Conduction is heat flow through a solid material. Convection is through gases, air, and homes. And radiation is a hard one to explain, but it's surface to surface with nothing else carrying the heat. So the best example I can give is the sun's up in the sky, and we are the planet Earth. Planet Earth is a cool surface compared to the surface of the sun. So the heat of the sun travels through the vacuum of space as radiation. The cooler surface of the Earth absorbs that radiant heat, and that's the best example I can give of radiant heat transfer. So those three forms of conduction are all experienced in our homes. Here's a picture of those three forms of heat transfer. Here's a picture of conduction, right? What's going on here? We got a house. We're looking at a normal picture of it. We look at the same house with an infrared image, and you can see something's missing here. What didn't they do to that wall assembly? They didn't insulate. You can see it. It's performing about as well as the transom above the door, right? You can see actually probably looks like some studs in there. You know, what do you think happened?
Just failed.
Everybody else.
Doorbell, got to pull the insulation out, or whatever that is.
The doorbell artist needed a lot of room to wire that thing. Outside. We're standing outside. And it's the winter, so they're heating inside, and it's cold outside. Yes, sorry, so set that up. Yeah, so we think it's possible that, you know, some people say maybe there was going to be a window there and they changed it. That's possible. Maybe this guy that wired this in, you know, tore all the insulation out, trying to get, how am I going to wire this doorbell? That's possible. We also think maybe y'all seen a shower stall, basically, that comes out and it's just installed, they put it in framing. You see that all the time. They come out, they set that on that exterior wall, then the insulator comes later and they hang the insulation behind it. And so, you know, that's also potentially what's going on here. But regardless of how it happened, you can see that's a big thermal bypass in that wall. Here's another one. Our regular picture, our infrared image. I'm inside the house. It's cold outside. We're heating the house inside. What's going on right here? Air leakage. Convection. Air leakage under the bottom plate in that wall assembly, right? So you can see there. What didn't they do? They didn't air seal the bottom plate. They didn't put down a Vita caulk or a gasket before they put that bottom plate down on the slab. All right. Radiation. Our homes really experience radiation primarily in two places. Our attics and our windows. And again, that's surface to surface. So the sun, big, hot, glowing ball of gas in the sky, looks down, sees the earth, warms the earth, looks down, sees our roofs, heats up our roofs, looks down, sees into our windows, sees interior surfaces, warms up the interior surfaces of our house. That becomes load that we have to reject with our HVAC system, right? That radiant heat transfer. Y'all ever had a house or an office and you had a window in a room that faced west? And you get to be summer and you're in that room with that west-facing window, and what's it feel like in there? It sucks. It's hot. You're just loading up on heat gain, And you know, your system can't keep up with it. It's not designed for the amount of BTUs that are blasting through that window, warming up that particular zone of the house. And I think just about everybody's experienced that, you know. August, 3 p.m., west-facing window, that room's going to be pretty uncomfortable because you're getting a ton of heat gain. And so our houses, when they get hit by the sun and either allow heat gain in through their windows or absorb heat gain in through their roofs, through their attics, that's taken on load that has to be rejected by the mechanical HVAC system. We're looking here at an infrared image of a roof deck. 168 degrees surface temperature on that roof deck. That's hot. You can't really put your hand on 168 degrees. You think of about 165, you'll pull your hand back immediately when you touch it. So those roof decks are basically scorching hot. Our attics and our roofs are really interesting places that experience all three types of heat transfer in homes. From the sun to the roof shingle, 1 to 2, is radiant heat transfer. That roof shingle is what? It's granular, it's black, it's leaned back to take lots of solar exposure throughout the day. It's basically a perfectly designed solar collector. So it gets really hot, absorbs, absorbs, absorbs. How many of y'all have gone up? I've done this several times. Every time you do it, you're like, I thought I'd learned this before. And it's like July, and you have to go up on a roof, and you get to the top of the ladder, and you put your hand on the shingle, and you're like, how many times have I done this? You know, every time. You're like, I know I'm supposed to wear gloves. It'll burn you. Super hot. This surface gets really, really hot. Then the heat builds up, and it starts to conduct from hot to cold. These surfaces are cooler. So it conducts through the roof assembly. Then the backside of this roof deck does what? Like I just showed you. It gets really, really hot, 160, 170 degrees surface temperature. Heat starts to radiate off the backside of this roof deck. It sees these other surfaces, your insulation, your air handler, your ductwork, your framing. It starts to warm up these surfaces. And then eventually the air temperature builds up in the attic. It gets to be 110, 120 degrees up there. And then what do? We use convection to try and cool that roof with venting, right? Hot air goes out the top. It's made up by cooler air coming in the soffit vent here at the bottom. So in the summer, we're sending 125 degree air out the ridge vent, and we're bringing, 90 degree air in through the soffit vent. And, that's the idea, that we're trying to cool that roof with the natural force of convective air. And then sometimes you see people do silly things like, y'all ever seen somebody put a power attic ventilator up there? Will that cool the attic? Oh, absolutely it'll cool the attic. What's it going to cool the attic with? In the second floor conditioned air. That's exactly right. It'll help. So now you're basically depressurizing your house by depressurizing your attic. You're sucking conditioned air out of your home and into your attic. You're wasting energy. You're setting up a bad, air quality situation with a house now under negative pressure. You've created more uncontrolled air changes. You're putting your home under negative pressure, which we certainly don't want to do in a warm, humid climate in the summer. But hey, your attic is now 10 degrees cooler. So we think power attic ventilators are actually a really bad strategy. If you're going to vent passively. Power attic ventilation is actually banned by the current Georgia Energy Code, with the exception of solar-powered power attic ventilators. But don't do it. It really is not a strategy that benefits the home in any way. And it has all these other negative effects. Plus, you're using energy at peak, right? You're running that fan when it's hot. And when it's hot, that is when the utility has the maximum demand for energy, because everybody's trying to cool their homes. So power attic ventilators is a bad idea. All right, so why would someone spray foam a house? It costs 2 to 3 times more, but it seems like it works pretty well. And people often ask us why. And the real answer is that you get complete coverage, and that this insulation product is also an air barrier. So when I'm insulating and air sealing a home, and I'm doing a traditional bath product, insulation job, or maybe a blown product like a cellulose that's not an air barrier, I've got one trade, really multiple trades, that have to come through and seal all the holes. And then I've got a separate insulator who comes through and puts in insulation. He's probably going to try and seal some holes as well. But then I got other trades who come through later and they punch additional holes. And so I got all these different people that have to be coordinated in completing the air barrier, sealing the air barrier, installing the insulation, resealing the air barrier, and then continuing to fix holes that are punched in the envelope for things just like duct boots that punch through drywall, right? If my drywall and my ceiling is my air barrier, and I punch a boot through it for HVAC, I punched a big old hole in my air barrier, that has to be sealed as well. That doesn't happen until final, right? So everybody along the way has to be air sealing to make your insulation work effectively. All of these trades have to be coordinated. The nice thing is that you've got one installer that puts in complete insulation, and that insulation is also your air barrier. And then in addition to that, one of the big benefits is you bring that ductwork inside the conditioned space. Because instead of operating in a 120-degree attic or a 125-degree attic in the summer, you're now operating in an 85-degree space. And that really helps your ductwork and your air handler work better.
Is it still true that the people who install foam are not trained or certified in any form of that?
It's a good question. It's something I was going to sort of touch on at the end. It used to be, if you go back 15 years, there was kind of one big supplier, Iceni. They were making a lot of the foam, and they had really good quality control and really good training programs, and you could pretty much know if it was a spray foam job, it was a good install, because they were well trained and good quality assurance. That has changed. There are a lot of manufacturers, a lot of people putting in foam products, and you'll get an insulator that they'll put in a fiberglass product, they'll put in a cellulose product, they'll put in a foam product. They got a rig in the car, they'll put in whatever type of insulation you want, and the foam products are made by a wide variety of manufacturers, and there is no longer the quality control and training that there used to be for those installers.
have gotten just completely off track.
And because of that, we see a lot of bad foam installation. And it didn't used to be true. 10, 15 years ago, foam job was probably going to be done pretty well because there weren't very many manufacturers making the product, and they were training the installers really well. Today, anybody can put in foam. There's lots of different manufacturers, and we see more problems because the folks aren't as well trained on what you have to do to get it in right. And so I've got a slide that comes up, I forget where, a little bit, that says, really, this insulation should be inspected on a new home. And that's true for fiberglass, it's true for cellulose, and it's true for sprayed foam. And it needs to be applied right, or you're not going to get effective R value. And you can mess up any type of insulation installation. It can be done. I've seen pictures where they sprayed the foam and either the mix was bad or the surface it was applied to was too cold, and basically the foam didn't bind well. It shrinks up, and they drywalled it up. You come in and hit it with an infrared camera, and you can see that even though it's a spray foam wall, it's got tons of heat bypass through it because they did a bad job with the installation.
What's the fix for that?
Take out the drywall, put more foam up, do it with a good mix, do it when the temperature conditions are right, and fill in the gaps that were created by the poor job that was done the first time around. It sucks. Yeah.
I'm not quite sure what the answer is. I know we got all of these rules and everything for the energy code. Every new house that I do, I can write up to where the insulation is not continuous, it's not touching the subfloor if I'm in the basement. And I look at it and I say, how in the world are they supposed to do this with all the penetrations and wiring and plumbing and ductwork? I mean, what's the answer? I mean, it just continues to, I write it up every time, but it's like, the next house I go to, it's going to be sunny.
Honestly, the real answer is set yourself up for success. If you want to do an insulated ceiling and you have a crawl space, if that was my house and I was building a new house and I was going to insulate the ceiling and I had a crawl space, I would put my duct system and my air handler in the crawl space. I would do a sealed crawl and I would insulate those crawl space walls. It's a great operating condition. You're ground coupled. That ground coupling helps cool the house. It's actually a free cooling feature. The equipment's going to operate really efficiently down there because it's going to be pretty steady, operating temperature for that equipment to be located down there. And then I'm not going to make penetrations in my drywall ceiling. and I'm going to caulk my drywall where it butt joints in the ceiling, and I'm going to caulk it where it hits top plates, and I'm going to avoid penetrating my drywalled ceiling. If I were building the house, that's how I would do it. And the name of the game is complete insulation coverage and complete air barrier. The problem is people don't really think about that. They don't think about the drywall and the ceiling as the air barrier.
A totally new concept about how to build.
Yeah, and so, I mean, that's the problem. You can do any installation correctly, but fiberglass in particular is the cheapest product, but it requires the most labor and the most attention to detail to be done properly. But what happens? You buy the cheapest product and you pair it with the cheapest labor source, and you get poor quality installation. And that's what's going on in the real world. And that's the three big things we found from the Energy Code field study we did were installation sucks. Nobody puts in high efficacy lighting, and ducts, especially ducts inside foamed roof lines, because they're not required by the code to be tested, don't get mechanically air sealed. And so we saw 20-30% leakage on duct systems inside spray foam houses because the word's on the street. You don't have to do a test, don't spend the labor and the materials to air seal this duct system. But it's still required by the mechanical code. So those were the three big things we found. Insulation is really crummy. Lighting, everybody's by and large still putting in incandescent light bulbs. They're not even getting to CFLs or LED for 50% of the homes. And duct systems installed in spray foam roof lines are not getting air sealed by mechanical contractors. And I get it. You don't have to do a test. That equals I don't have to air seal this duct system. It's cost. It's labor and material. So why do it if you're not going to have to prove it with a test? So how to fix that? I mean, what we're working on right now is working with code officials in jurisdictions where they're trying to do the energy code, and we're really talking to them about 8 key items that we looked at for the energy code field study that DOE decided drove the majority of the energy usage in homes, and we're really harping on the 3 areas of low compliance: the installation, the lighting, and the duct sealing. And we can only do what we can do in terms of trying to get people in local jurisdictions to enforce what is in the code. Because you talk to builders all across the Southeast, and they all say the same thing, which is, I do what the code official asks me to, because my job is to get the CO, and to get the CO on time. And so, you can teach them and teach them and teach them, but at the end of the day, their job is to manage subcontractors and get the CO on time. So it's really the code officials valuing this stuff and forcing the builders to do it that's going to affect change. Now, from a building science and a design standpoint, I can give you 10 different ways to build a good house. It's just that, how many people walk into a home and go, oh, forget what the kitchen looks like, my wife wants to see what's in the attic. Nobody, right? So, there's the problem. Granite countertops, fancy cabinetry, all that stuff, we'll throw tons of money at that stuff because nobody walks in with a new home and says, show me what your attic looks like, right? So that's really what we're up against from the building science, high performance home industry, is that it's not highly valued by the market and it's not well enforced by code officials. And so we really end up with the same practices that we had 20 or 25 years ago being built into homes today. All we can do is continue trying to tell people, guys, we can do that. Because I teach a lot of builders. You go to a home builder training, and the first question I say is, all right, raise your hand if you want to build a crappy home. Guess how many people raise their hands? Nobody. Nobody wants to build a crappy home. It just happens because the real world gets in the way, right? So we're continuing to try and push the industry. Anyway, this is a view of a spray foam roof line from inside an attic. This is a pretty decent job here. It looks pretty consistent in depth. These are the types of things you're looking for. We actually take a little tool, which is just like a barbecue skewer, like a bamboo barbecue skewer. We have it marked with inches, and we take that, poke it into the foam, makes a tiny little hole that almost kind of self-seals, and lets us know how many inches they've blown. We're looking for consistent coverage, and ideally, we're looking for these roof rafters to be covered as well. So this is a pretty good job, and if I wanted to know how many inches, basically it depends if it's an open cell or a closed cell product. Open cell product, you're looking 3 to 3.5 per inch. Closed cell product, you're probably looking close to double that, anywhere from maybe 6 to 7. The closed cell product, you go knock on it, sounds rigid, right? It's a dense foam, it's hard. The open cell feels a little more like a sponge. So, you know, if they sprayed this up there, you're probably going to see about an application of an R19 to an R20. So you're looking somewhere between 5.5 or 6 inches of the soft foam and, you know, 3 to 4 inches of the rigid foam. And that's what we'd like to see up there in that attic. Yep.
I believe the building code states that if the attic is used for storage, that you got to be concerned with combustible items. And the closed cell, it's labeled, I believe, so you don't have to have anything over it.
Yeah.
This is a situation with the open cell.
Interesting question. So it really today depends on the manufacturer of the foam, because there are some that mix into their mix fire suppression. And I'm not a chemist, so sort of how that works, but you can get a product that is rated essentially to be fire safe. Other products, other products need to be coated with an intumescent coating that comes on afterwards. And actually, the lady from the city of Atlanta that we talked to Wednesday, who was doing this exact retrofit in her house, said that the insulation bid was $4,000, and then the intumescent coating was another $4,000. And so we gave her another contractor to call.
Why would you go with the riches?
Again, I mean, that to me, it should not be double to do the recoat with the intumescent coating. That seemed way too high, so we gave her a couple other people she could call to get an additional bid. But the reality of it is, yes, you may have to cover this for combustion, for fire safety, and that depends on the type of foam you spray, that particular manufacturer's spec, and it's more likely that you're going to have to do something with an open cell foam than with a closed cell foam. But you really have to go look manufacturer to manufacturer and see what their foam is rated for.
Just back to the idea of foaming the ceiling. There's quality control, what you're talking about. There's also quality assurance. So when you walk up in an attic and you've got 17 different roof planes, chases, ceiling height, I mean, that's really, that's extremely difficult. You got one roof plane, one plane.
Yeah. This eliminates knee walls, which is a big advantage, and it eliminates, really, again, the problem of trying to use a single-sided air barrier, your ceiling drywall, as your primary air barrier for a product that requires to be installed with an air barrier, but you know you're going to be penetrating it with all types of holes, and you know you've got the biggest delta T that home is ever going to experience. It's trying to keep it 70 inside, it's 120 in that attic, it's a 50-degree delta T. That's about as big as the delta T you're going to see on the coldest winter days in a lot of homes. So, 20 to 70. And you're going to see that for months and months and months out of the year in our climate zone. So, there are a lot of advantages to going this route. Again, simplification, easier to know your air barrier and your insulation in one product, done in one pass by one contractor, and then it changes as we're going to look at the sort of thermodynamics of how heat transfer works in that home.
Bourke, I recently inspected a property in St. Ives, built in around, I'm thinking probably somewhere in the early 90s. And when I went into the attic, there was a foil material, basically, that was encompassed just about the entire attic area in all areas that you could see. And the foil material basically went up maybe 6 or 7, well, to maybe 8 feet. And then I could see beyond some venting. There was basically a full wide open gap between that and then a roof sheathing and the joist work and everything, the rafters.
Radiant barrier.
It's a radiant barrier, but it's not typically like what you see, the tech shield type material.
Yeah, it's a retrofit, and that's what, it's like a blanket. My next, I have a picture that these are in the same presentation with another one that has a retrofit. And that's just a radiant barrier retrofit where they come back in and staple that up to the bottom side of the rafters on the roof deck. And it's interesting because of how radiant heat transfer is surface to surface. unlike conduction, which is flowing through a solid and will find the thermal bridge, the pathway of least resistance, radiant heat transfer matters about surface area. And so a radiant barrier can be installed as a retrofit, work pretty well, and even if you don't have 100% coverage, you still get the benefit for whatever percentage gets covered by that radiant barrier. So a product like that is most likely a retrofit radiant barrier someone did. And if you have a traditional vented attic with HVAC equipment up there and insulation on the ceiling, a radiant barrier retrofit is probably the cheapest, easiest energy efficiency, retrofit you're ever going to do. You just go staple that thing up there, and it's going to drop your air temperature in your attic by 10 or 15 degrees. If you're building a new home and you're doing an insulated ceiling, I would absolutely do the pre-manufactured Tech Shield with the radiant barrier on the underside of the roof deck, because it costs a couple bucks more a sheet, and it will really bring down the air temperature in that attic, which reduces the air temperature, the ambient air around the equipment. And so, your duct leakage, if you have leakage on the return side, it's not as big of an energy penalty anymore. Your duct losses aren't as big because you're running 50-degree air through an R8 insulated duct, but instead of having to be 120 in that attic, it's 95, so you brought down that delta T. So it has a lot of benefits for very little upfront investment in a new home, and a very easy retrofit.
Along the lines of that barrier, if you put it, so you're trying to keep the air up there cool, so if you laid it down on top of the ceiling joist, you still have the hot air behind it?
People do that, and that will help in terms of the amount of heat that sort of conducts and transfers from that hot attic through to the inside of the house. One, it's not as effective in that location. You prefer to have it where it's trying to keep the backside of the roof deck from radiating all the way through, and where you're venting behind it, so you're expelling that air out of the house if you do it in that retrofit. And then the other thing is, if it sits up there like that, eventually it's going to get dust all over it. And this sounds crazy, but if it's no longer shiny, then it actually loses its effectiveness as a radiant barrier. So when they lay it on the flat, it gets dusty over time, and that degrades its performance. So I would go through the trouble of stapling it up, basically.
On the spray foam, how do you account for the ventilation requirement on the roof decking?
So, two ways. One is you can get a roof shingle manufacturer that will warranty a roof with a spray foam unvented roof assembly underneath it. And here's how you find them. You find a manufacturer who manufactures roof shingles, and they manufacture spray foam. And lo and behold, they will warranty their product installed correctly unvented. On the other hand, if I'm a manufacturer and I don't make spray foam, I make an alternative, more traditional insulation product, and I make a roof shingle, guess what? I don't want to warranty my roof shingle with somebody else's insulation installed. And so in order to get around that, I don't warranty an unvented assembly. Sneaky, but that's the gist of it. What kills a shingle?
Excess heat.
Heat, right? UV exposure and the thermal cycling between, oh, it's getting baked, oh, it's getting frozen in the winter. Those are the two things. Studies have shown that if you vent underneath a roof shingle or you don't vent underneath the roof shingle, it actually has very little impact on the lifespan of the shingle. I'm not saying it's no impact, I'm just saying it's very little impact because the primary factors are there anyway. They're the UV and they're the heat. And so if you want to do an unvented assembly, get a roof shingle manufacturer that warranties that. And honestly, if you're doing a retrofit and they've already foamed the house and then they need to re-roof, get a manufacturer that matches that. If you've got an existing, 10-year-old roof and then you're going to go foam underneath it, if you degrade 1% of the shingle life, okay, I'm going to re-roof a couple months earlier. I mean, the impact is largely overstated when you look at the building science of it, and it really comes down to, I make fiberglass and roof shingles, I don't want to warranty spray foam with my shingles. Find a manufacturer that manufactures both, they'll warranty an unvented assembly.
When somebody retrofits and puts in a spray foam under the rafter system, The recommendation is to take out the open ceiling fiberglass insulation alone.
Yes.
What's your comments? Is that the smart thing to do, or
Yes.
why is that the?
Indoor air quality. And good lead in to me getting to the next slide. And by the way, quick time check. What time is it? 2:15?
Just about it.
Okay,
Clock's passed.
so we're going to end at about 3. At this rate, about 3:50. At this rate, we'll be done about 12 o'clock tonight. So, pick up the pace. These are great questions. I'm just looking at the number of slides I'm on at the time and going, y'all want to have dinner? I mean, but all that said, to answer your question, we do recommend when they do this as a retrofit, they remove that insulation that was already there. And the real reasons are, one, this is no longer your thermal boundary, right? You've moved your thermal boundary up to the roof line, so that insulation isn't your primary thermal boundary anymore. And then the other is really indoor air quality. This is a very airtight assembly, and it's now inside your home, right? This attic is now inside the air pressure boundary of the house. So you've brought your attic inside, and if this has been an old vented, roof, I mean, if there's old fiberglass up there, it's friable. If critters have been getting in there, you got roach scat, rat scat, and urine. I mean, if you're doing this, pay the extra money to have that stuff removed, and it's really for indoor air quality as much as anything else. Because it's no longer your thermal boundary, and it's likely to not yield good indoor air quality if you leave that stuff inside the home.
So you're saying the installation I saw in an old house a few months ago, where they actually came in and sprayed the spray foam over the old insulation, was not a good installation?
I lost the microphone. That made me so sad. No, I mean, and this is where, coming from the high performance, I've knocked this thing off several times. I hate loud leaders. I'm doing it for y'all. We had an architect last year called us up at Southface, knew Southface very well, had an older home in Norcross he had bought, wanted to renovate. I feel like I'm really loud now. Like crazy loud?
You're good.
Okay. Had an older home in Norcross he wanted to renovate. He said, you should do earthcraft. I said, listen, I don't really believe in certifications. I'm a designer. I believe I can design a perfectly good house, and I don't need a certification. I said, well, I might disagree with that a little bit, but I'm not going to try and force something on you don't want. What can we do to help? He said, can you send somebody out, look over my house, and basically give me a list of opportunities to improve that we can consider as part of the renovation? I said, sure, we can do that. So Mike and I went out, charged him a little bit to come out for a half day, look around his house, and just give him basically a list of things that he could do. And I forgot why I started telling this story. What was your question?
Over the old existing insulation.
Over the old existing insulation. Basically to say that, while not ideal in my world, because he didn't go all the way through with the certification, which would have included inspections and quality assurance and more consultation on the design, at least he brought someone out and said, tell me, what do I do in my crawl space? Tell me, what do I do in my attic? Tell me, what are my best options if I'm going to replace my HVAC system? And we got to talk about all this stuff. A complete air barrier, combustion safety, fresh air ventilation. Where is your thermal envelope? You're improving your thermal envelope. You don't have to go back in with, you've currently got, 2 systems and, 10 tons or whatever. You're going to be able to downsize that. You're going to be able to zone it this way and talk through all that. And at a minimum, that was a really good consultation. Because what you saw is an example of someone spending money on something that has very little value. And that's not to say it would air seal and it would add insulation, but why in the world would you apply that product in that way when, for probably only slightly more coverage, you could seal the attic, assembly and reduce the air temperature up there? I guess I could say if they wanted to, if they didn't have equipment up there, they could foam on the roof surface and that would be fine. But the flip side of it is I would still take out the old, and we often see in that world what they do is called a flash and batt, where they'll take out the old insulation, they'll put down like a 1/2 inch or 1 inch of foam, just basically to air seal and provide a little bit of R value, and then they'll dump a more affordable product on top of that. And That would be a really good way to air seal the ceiling plane in an existing home. But I would only consider that if my mechanical systems were entirely in the basement. If they're in the attic, I would absolutely foam the roof line because I want to reduce the operating temperature around that. And I think that seeing stuff like that in the real world is really an example of people knowing they have a problem and calling a contractor who comes out and says, oh yeah, let me do this thing for you. And they may or may not be getting the best advice. So that was my long rambling story to say, it would really be great if people who are about to spend $2,000 or $10,000 or $20,000 of an investment into their home would get a good, well-informed consultation that cost a couple $100 before deciding to spend $5,000 or $10,000 or $20,000. Unfortunately,
Does that?
anybody could do that. The problem, I mean, anyone who's informed could do that. In our industry, it's usually BPI, building performance contractors that are certified and know how to assess a home. The problem is, just like granite countertops versus good quality insulation, a lot of people don't value spending an extra $500 or something to bring an expert out to tell them the best way to spend their money on their bigger investment. They bring out a contractor or they already know what they want, and they just get something done on their home. Maybe it works great, maybe it doesn't, but they called somebody out most likely because they have a comfort issue or an energy expense issue, and maybe they're getting a good solution, maybe they're not. Jim?
Just briefly, my brother had his roof on. He had the place open up, had the drywall down, still had a lot of insulation up there. He's a landscape designer. He modified a leak blower and hooked up some some flush pipes, some Home Depot flush pipe, and ran it out to the dumpster. So, there's ways to do it. You're just creative enough to
Yeah, get that out of there. All right, so I'm going to pick up the pace a little bit, but please keep asking questions. I just don't want to go over on time. So questions we commonly get, like, will the foam increase or decrease the size that I need for my HVAC system? And, the reality is it depends. Why? Well, we're going to get a tighter house, but we're going to have more envelope surface area. We're going to have lower R value because they're not going to apply an R30 spray foam or an R38 spray foam up there. They're going to do about an R20. And that has to do with the price of the product and the law of diminishing returns, which means for every R, every next R you add, you cut conduction half as much as the previous 1R, right? So your first 1R is the most valuable because your R2 has half of the effectiveness of your R1, and your R3 has half of the effectiveness of your R2, if that makes any sense. So the law of diminishing returns says once you get to about an R20, you've dealt with so much of the conduction that to spray another R10 that's 50% more cost is not going to get you a significant reduction in heat conduction through that assembly. So R20 is about the standard spec, and it's an expensive product. So they tend to do about an R20, so you're going to have a lower R value, and you're going to increase the volume of the home. Why does it work? Well, all that other stuff we talked about, right? You're air sealing, you're bringing that equipment in and out of that oven for operating temperature, you're not venting your attic in the summer, and it just works as a better assembly.
If we go with the left, now the roofing contract, you got a board also. How are we going to, 5 years now, find a roof leak with this out there?
That is a common concern. I would say a couple things. One, I hate to say this, but if your roof leaks, that is not your insulation's fault. I mean, that's bad construction by somebody else. So it's sort of like blaming the wrong entity. If your roof leaks and you can't find it because of your insulation product. Yeah. The other thing is, people say, if you have an open cell spray foam, it is not a water barrier, it's not a moisture barrier, and you can see a water spot. It will pass through it. If you have a closed cell, people concerned that it runs and it rots off the roof deck, but honestly, closed cell spray foam is structural. So to some extent, you might be better off with your rotted roof decking with a continuous spray foam, closed cell spray foam under it, because it's structural. So, again, it's a problem that you have to think about, what about roof leaks? But I'm not going to blame my insulation because my roofer did a bad job. I understand it's harder to inspect. That is probably a real issue. All right, so y'all probably seen this equation before. Heat flow is Q is heat flow. Q is a function of U times area times U is resistance to conduction or conduction. R is resistance to conduction. U is a measure of conduction. Area is the area of the surface, and delta T is the temperature across the surface, right? So what's my outside temperature? What's my inside temperature? It's my delta T. It's 70 inside and it's 95 outside. That's a 25 delta T. It's 70 inside and it's 40 outside. That's a 30-degree delta T. How much area, surface area, is experiencing this delta T? And then what is my, basically, conduction across that plane? So Q equals UA delta T is the equation for heat flow that we use in the building science world. And this is why, if you look on paper, and you have an R38 applied to a 1,000 square foot ceiling, and then you look on paper and you have an R20 applied, to a 1,200 square foot roof deck. On paper, it looks like the roof deck is not going to perform as well as the insulated ceiling, right? Because the insulated ceiling has less, keep hitting the wrong button. It has a better U, it has less area. On the other hand, it has a greater delta T. That roof deck has a lower delta T, but it has a worse U and it has a greater area. So on paper, people can look at a spray foam roof design and say, oh, it's going to have more conduction. It's going to be a worse performing assembly than if we insulated the ceiling. What's the problem with that? All this other stuff I've been talking about. In the real world, how well is your ceiling actually insulated if the product's not in contact with its air barrier? How well is the air barrier working when we punch 1,000 holes in it? What's the delta T? Well, 70 to 120 is a much bigger delta T than 85 to 95 if you're talking about outside ambient versus indirectly conditioned space. So we have actually had engineers who are like, explain the spray foam roof line to me because I don't understand, because if I just do Q equals UA delta T, the spray foam roof line doesn't work as well as the insulated ceiling. And the answer is, it's called reality. It's called how things get built in the real world. It's back to that one installer, one pass, air seals and insulates in one product and reduces the operating temperature of the air around your HVAC system versus trying to insulate on a flat ceiling and trying to make that a good solid air barrier, and then what's the operating temperature that your HVAC equipment is, and what's the delta T across that surface. So the reality of why spray foam really works is that it covers up so many of the problems that we have in the real world of trying to create that continuous air barrier and continuous insulation barrier in a home. All right. Will this impact your question?
When it comes time, when you're replacing the roof, you find a piece of roof decking, let's say a 4x8 panel, that needs to be replaced because of rot or for various reasons, past leaking. What happens to the spray foam that's stuck to the bottom of that?
I would basically cut the foam out, remove the decking, replace the decking, spray another pass of foam. I mean,
so you have to call you back out, set up and spray it back on.
Well, anybody can. I mean, any insulation contractor would can put in foam these days. So it'd be like any other thing. If somebody gets a water leak and their ceiling collapses in their living room because they had a plumbing leak that collapsed their ceiling, well, you're going to put the drywall back, but you're also going to have to put new insulation in, right? So it's the same problem. If you damage that roof deck and you got to cut out that damaged roof deck, and that's where your insulation is, then you got to put more insulation back.
Well, not necessarily the ceiling insulation, on, regular bats or blow-in. A small leak, the water will evaporate on summer days, and then usually with a heat loss gain ratio, it will.
If my bad insulation got waterlogged, I would replace it. That's a mold growth, mildew, disgusting problem waiting to happen. And I guess my point is, if you have damage that occurs in your home and it damages the insulation, then you probably are going to have to repair the insulation as part of the repair, and I wouldn't consider that to be unique to spray foam. But that's just my take on it.
Okay.
On the side of, have you ever, or has anybody looked at, when spray foam goes in, if you're in a high radon area, finding that the house is more susceptible to higher radon levels and a house with normal insulation?
You could see that problem because you made a tighter envelope. In general, the state of Georgia is, and specifically the metro area, is a high radon zone. Any new home, I would recommend a passive radon vent system that's pre-wired to become an active radon vent system because it'll cost you a couple $100 to put in at the time of construction, and it is basically protecting human health. And I think it's a good investment. And in an existing home, it can be retrofitted, but it's a trickier retrofit. But definitely, you could see a tighter spray foam house that then has an elevated level of radon because it's a tighter home. That said, lots of times we're reducing uncontrolled air changes and we're putting back in mechanical ventilation. If I do a spray foam roof line job correctly, I'm going to baseline with a blower door test before I do it. I'm going to foam the roof line, and I'm going to do a blower door test afterwards. And there's actually basically a way you can determine then how much additional ventilation you need. In my world, I would ventilate to ASHRAE 62 anyway, and I would put the house under slightly positive pressure, which could help me mitigate soil gas issues. But it is potentially possible that you could make a house tighter and then have a greater radon. It's certainly
I've
true.
seen retrofit in every case north of Georgia 20 where the radon levels are higher. And if we not have the fresh air system, the radon levels have gone up.
We're going to talk about this. Two things in particular. When you do a foamed roof line, particularly as a retrofit, you need to add ventilation air and you need to eliminate atmospherically vented combustion appliances from the breathing zone. So you can't have, an 80% furnace or an atmospherically vented water heater inside that spray foam roof line. Those things have to be dealt with as part of the renovation. I mean, it's bad mojo to go any other way. That again, this goes back to that whole idea of when someone's going to make a $10,000 or $20,000 investment in a renovation of their home, why they don't have someone give them recommendations on how to do it right for a $500 consultation up front versus bringing in a contractor who, what do I do? I put in insulation. What do? I make cold air. These two trades should be talking to one another. They should be coordinated in the house as a system. Too often we see, somebody comes out to fix a problem and they know what they do and that's how they fix the problem. Whether it's a bigger unit because, I'm uncomfortable. Or it's, they spray foam the roof line, but they don't consider combustion safety and they don't consider, have I changed the tightness of the home and am I going to see a radon issue? If you have a crawl space, and crawl space homes, slab homes aren't as susceptible to radon, but it can happen. Lots of times it's crawl space houses. If I was foaming a crawl space house, I would really consider a closed cell spray foam on the underside of that floor because it's an air barrier, it's going to stay in place, it's a moisture barrier, and there's a lot of ground moisture. We're supposed to put plastic down, but a lot of times existing homes don't have complete plastic coverage. I would still do that. But if I was going to foam a house and money was no object, I would not only foam the roof line as a retrofit, I would do a closed cell spray foam on the underside of the floor in a crawl space, and that's going to help a lot because then you can go in and you can just vent that crawl space with an active exhaust vent, and you're going to really mitigate the potential for radon issues. If it's slab on grade and you have a radon issue, it's a lot more challenging. It can be done as a retrofit. You're just probably looking, a couple $1,000s versus a couple $100s. But again, if you go in and you spray foam that roof line and you add in a mechanical outside air ventilation system and you size it right to put the home under slightly positive pressure, you should mitigate the potential for radon risks. But again, building is a system. Is your guy who foams the roof line thinking anything about the HVAC system? Only if someone's talked to the homeowner before to make them well informed.
All right, so when you spray the roof, the back of the roof decking and everything, do you shut down close off the gable vents?
Yes.
The ridge vents?
Yes.
Okay.
No gable vents, no ridge vents, no soffit vents, no
Yeah.
turtles. It is now an unvented attic assembly. In fact, if you imagine, if you vented like you would in a traditional house, you would completely bypass what is now the thermal envelope because you've provided an air loop pathway to basically bring outside air in around your new thermal boundary.
What, you got a HVAC system in the attic?
Sorry, I got two people talking at once. I'm
All
going to go back here and then I'll come down here. What was that follow-up question?
HVAC system in the attic? The vent for the emissions gas vent?
That's what I'm saying. If you spray foam a roof line, you no longer can have an open combustion piece of equipment in that attic. So you
Okay.
also have to swap out an 80% furnace. You either got to have a direct vent or a sealed combustion furnace.
Or electric furnace, so heat pump?
Or heat pump. I would not put in an electric furnace as the primary heating system for the home.
Okay.
You can't in Georgia legally, but it's too expensive. A heat pump, on the other hand, could work just fine. I actually have a slide coming up in a minute. This is really interesting. When you spray foam a roof line, you bring down the balance temperature at which the heat pump can operate. So your heat pump can make hot air at colder outside temperatures in a spray foam roof line house. And I'll go in that.
Okay.
Obviously, if you spray the roof line, you're going to have to spray the gable wall as well in order to create the membrane.
Yeah, so you would seal that all the way up. Yeah, absolutely. All right, so will doing this affect the load on the house? And, the answer is yes, and then the answer is, one of the biggest things that affects whether or not a load calculation is done correctly are these things called the design temperatures. And these are in ASHRAE, and it says, and this is from Alabama, sorry, but it tells you the winter and the summer design temperatures. And if you can only if you have access to a load calc, and you're only going to look at one thing, this is probably the first thing to look at, because it's the easiest thing to tinker. I want a little more load, so I'm going to make my summer design temperature in Huntsville be 97 instead of 92. All of a sudden, I need a bigger HVAC system. So if you have the chance to look at load calcs, you can look at design temps, because these are basically set by ASHRAE, and you can see whether they've used correct design temperatures. It's one of the first things and easiest things to fudge if you're trying to manipulate the load calculation. The other thing is look at your surface areas, because Q equals UA delta T, area matters, insulation level matters. So if I'm trying to manipulate my load calculation, I may also increase or decrease, probably increase my shell area to try and get a bigger system on the house. So look at the insulated surface areas and see if they're accurate to what's actually on the plan or how the house is actually designed. And then look at infiltration rates. A tight house, which is what new homes are, is actually an input. You could go with a leaky house, and that's going to increase the size on the HVAC system. So design temperatures, surface areas, and leakage, infiltration on the home are the three easy things to manipulate on a load calculation if you're basically trying to make the software spit out a predetermined number. Just those things. All right. Again, I mentioned this earlier, but this is required by the code. So they are supposed to do a load calculation, and they're supposed to size the equipment to that load calculation. They're supposed to provide that documentation to the building official, and they are legally obligated to do this. Again, one of the most rampantly ignored things in the energy code. And this is just a very exciting screenshot of what the ACA Manual J software actually looks like. You see it's got loads, it's got areas, it's got BTUs for heating and cooling, it's got U factors. So again, that stuff that I'm telling you, U factor is the inverse of R value. You've got areas, you've got heating and cooling demands, you've got perimeter areas, and all of this summarizes up and spits out a load calculation. I don't expect that y'all are going to have access to this. It's a tough one as a home inspector. You don't have the same authority that the code official does, where they could demand that the builder produce this. I don't know if y'all are really in a position to demand that they produce this. And it's challenging because I really think the majority of our industry is not doing this correctly. Does anybody here actually do load counts themselves? A couple guys. We've thought for years about teaching a class on this at Southface. We just don't know. It would be great for everybody in our industry to know how to do this. Sort of don't know what the interest level in reality is. So the foam insulation could increase the size of the HVAC system because, we've increased the surface area, we've reduced the R value, and we're going to have to add ventilation back into the home. So theoretically, again, someone could say, oh, doing this foam roof line is going to make me put in a bigger HVAC system. But in reality, the home is tighter, the insulation coverage is typically better. The foam actually holds its effective R value better over time than the fiberglass products do. And the big one, the ducts and equipment are now inside the thermal envelope, which means instead of operating in 120 degree air temperature during the summer, they're operating in an 85 degree air temperature. And this makes a big difference.
On a dollar to return ratio, how long does it take to the difference to be made back in
That's a good question.
reduced energy costs?
I work with a lot of engineers, and so I know the answer to every question is, it depends. And it's so generic, I really can't say, because it's individualized to that house, particularly return on investment, what are your current utility bills? How much foam do you have to spray? Do you need a new HVAC system? Are you going to do the new HVAC? I'm answering the question.
Yeah, that's good.
Okay. All right. It depends. Because there's a lot of variables. All joking aside, there's just so many variables. It's hard for me to particularly say, this is what your ROI will be. What's the ROI on granite countertops?
How much radon is in a granite countertop?
That's another good one. Yeah, it's like, do we have a radon problem in this home? I don't know. Maybe it's the 400 square feet of granite countertop off-gassing in your kitchen. Who knows? Very good. All right. And again, factors that affect comfort. Why do we put all this crap in homes anyway? I was thinking about this morning when I was getting ready in my kitchen, putting this presentation together. Butcher block countertops. Putting this presentation together, and I was watching some deer run through the backyard, which was kind of cool. And I was like, what are you guys doing out in the middle of the day, whatever? And I was thinking about, why do we do all this stuff in our homes? Why do we spend energy to condition air, and why does that make us put in insulation and blah, blah, blah? What's the answer? Comfort. We want to be comfortable. And you go back 50 years, and what comfort meant was completely different, right?
Shoot,
Yeah. My background is in historic preservation, right? That's what I did before I came to Southface. It's what I studied in college, because I was interested in basically how people, manipulated the built environment, and what we did with buildings, and what we did with the way we built things around us. And the reality is, we used to build really energy efficient homes, right? Because they didn't have HVAC systems in them, they didn't have electrical lighting in them. What did they do? They provided shelter from the environment, and they provided security for people.
12-foot ceilings.
And high ceilings and big overhangs and porches. There's this really interesting book, if y'all ever get a chance to read it, called The End of the Long Hot Summer, that is about the cultural impact of air conditioning on the South. Because we used to have these really communal, people had big front porches they sat out on in the summertime.
Right.
We designed our houses with big overhangs. We shaded our window. We did passive solar. We had high ceilings. Eventually we got electricity. We put in whole house fans, right? We throw open the windows, turn on the whole house fan, and get huge air changes as a way to provide comfort, right? So, do what? That was before Facebook. So you go back.
That was before TV.
Before TV. People used to have completely see different expectations of comfort, right? What are comfort expectations today? You walk into a house and it's 70 degrees and 50% relative humidity, no matter what the heck is going on outside, 24/7, 365. That's what people expect from comfort today, right? Perfect conditions inside their home, regardless of whether it's 40 degrees outside or 90 degrees outside, regardless of whether it's a drought or it's pouring down rain, whatever. They expect perfect interior conditions all of the time. And that is really what has driven us to increase our energy use to try and get better comfort, to meet modern comfort expectations. And that's what's driven us to say, well, we got to have more efficient equipment and tighter envelopes and better insulation. Hey, you want to build a zero energy home, don't put in electrical lighting, don't put in HVAC. Hey, it's going to be the greenest home ever built. Is it going to meet today's comfort expectations? Heck no, right? So I mean, just all of this stuff. Why do we do all of this stuff in our homes? And the reality of it is we're trying to create comfort. And comfort is a factor of air temperature, it's a factor of humidity, airflow, and surface temperatures, right? If y'all ever walked into like a parking deck and it's a big concrete structure and it might be, 80 degrees outside, but you walk into that parking deck and it feels cool, but it's a vented parking deck, it's wide open. The reality is all of those surfaces around you are mass, and they're holding essentially energy. Like a mass wall is a big storage bank for thermal energy. And so those surfaces stay cool even when the temperature outside gets warmer. And they have big thermal lag. And so you walk into a parking deck and it's 80 degrees outside air temperature, but it's cool in the parking deck. Well, that parking deck's got lots of air blowing through it. The air temperature is not that much cooler, but the surface temperature is dramatically cooler, and your body radiates heat to the cooler surface, right? Wherever our bodies go, we're either absorbing radiant heat from the surfaces around us or putting off radiant heat to the surfaces around us. And so surface temperatures, airflow, air temperature, and humidity have a big impact on comfort. And, here's the dirty little secret. It ain't the heat. Guess what? It's the humidity, right? This is looking at actual temperatures from a bunch of locations in the southeast, and these happen to be in Alabama, but Birmingham is pretty much Atlanta, Huntsville is pretty much north, Georgia, Montgomery is pretty much middle Georgia, Mobile is more coastal, but anyway, you get a general idea of the southeast, and you look at observed temperatures, and our ASHRAE design temperatures are somewhere in these ranges right here, where the number of hours of the year that we're above those design temperatures are very minimal, right? So it's not the heat load that makes us uncomfortable in our houses. I mentioned this earlier. Our HVAC systems are really good at making cold air, right? Bam, cold air. The problem is they're not very good at dehumidifying. And the comfort factor that we're often trying to deal with inside our homes is relative humidity, more so than it is temperature. A 70-degree house with high relative humidity is clammy and uncomfortable. A 75-degree house with 50% relative humidity feels great. And so what we really find is that reaching temperature set point with equipment and having equipment that can operate effectively up to the ASHRAE design temperatures and down to the ASHRAE design temperatures is not a problem. Managing the indoor humidity level is a big problem in our climate zones. And that's really the comfort factor that's driving a lot of our issues. Not to mention mold and mildew and indoor air quality problems. So the old saying is true, in the South, it ain't the heat, it's the humidity. And if the reason we're doing all this stuff to our homes, spending this energy, doing this air sealing, doing this insulation, doing more efficient systems, is because we care about being able to walk in and have it 70 degrees, perfectly comfortable year-round, it ain't the heat, it's the humidity that we're really trying to deal with. And oversized equipment, improperly sized equipment, load counts that aren't done, loads that are, not reflective of what's actually installed in the home, not only are they not going to provide good comfort, they're most likely not going to provide good comfort because they're not going to dehumidify effectively. Remember what I said at the beginning? You got to get that interior coil up to steady state, solid state operation before it starts wringing moisture out of the air. About 10 to 15 minutes of runtime before it starts to dehumidify. So in order to dehumidify effectively, what you want is lots of air slowly drawn over a coil for a long period of time. So the best comfort is actually provided today by variable speed equipment, where we can slow down the speed at which air is being drawn over that coil, and we take longer to reach set point inside the house, and we're effectively dehumidifying, and we're getting lots of runtime on the equipment. So the real future of our HVAC industry says, I'm a contractor and I don't want callbacks. I don't want people calling me because on the one day of the year, or the 2 or 3 days of the year, that it is 97 degrees, and the thermostat is calling for cooling, and the HVAC system is running and running and running, and people are saying, I can't get to set point. I don't want that callback. So I want to oversize my equipment, because if I can always hit set point, then people are going to say, well, the system works well. But the reality is, you're already oversizing the equipment based on the temperatures that we normally see. And if you oversize even more, you don't effectively dehumidify, and you don't create good comfort. And people don't realize that they're uncomfortable because they are short-cycling their equipment and they're hitting set point too fast. What fixes all of this is multi-stage equipment, which is what is coming into our industry, which allows you to have a blower that can move the air at different speeds. It's more energy efficient, it provides better comfort, and basically allows you to oversize the equipment so that if it's 95 degrees outside and they're having a pool party and they have the sliding glass door open and they're running the air conditioning system, well, okay, we can actually handle that load because we're way oversized. But then every other day of the year, we can stage down the equipment, we can stage down the blower, and we can run to meet that actual load that's on the house. So the best case scenario really is, fine, oversize your equipment, but put in variable capacity and variable stage blowers so that you can meet the load in that house at any actual condition. And then you're going to get the best possible comfort. You're also going to pay, what? The most upfront cost. But the reality of it is, that is the best possible system, and that's really where our industry is going in the future, is variable capacity equipment, so we can meet, we can oversize to meet any of these ridiculous loads that we're hardly ever going to see, but we can operate efficiently for the loads that you're actually going to see 75 or 80% of the time on the house. And you get better dehumidification in the process.
And this is part of the system itself.
Yes.
The blower itself within the system.
It's a combination of the variable speed on the blower and multiple stages on the outside compressing unit. Yeah. And then I teased this a little bit earlier. One of the interesting things is, if you have a heat pump, there's this magical thing called balance point. Does this ring a bell? It's the point at which essentially the heat pump starts to struggle to meet the load. Because what a heat pump does is uses refrigerant to make heat flow backwards. So when we're in cooling mode, it's taking heat out of the house from an indoor coil, it's pumping it to an outdoor coil, and it's rejecting it outside. And the hotter the air temperature gets outside, the harder it is for the heat pump to reject air to the ambient heat. On the flip side, in the winter, when we're heating, the heat pump is absorbing heat from the outside through a coil, running it to the inside, and rejecting it into the house to try and warm up the house. And at some point, the heat pump gets to the point where it starts to struggle to meet the load on the house. So we're looking at basically BTUs an hour here, we're looking at temperature here, we're looking at the heating capacity of the equipment, we're looking at the load on the house, and we have this magic thing called balance point, which is where the demand for heating starts to outstrip the ability of the heat pump to meet the load. And if you improve the thermal envelope of the house, so this would be like our average home, this would be our improved thermal envelope, what you see is this heat pump system, right here is balance point, where the load and the curve of the load and the curve of the capacity of the equipment meet is about 35 degrees. So if you drop below 35 degrees, what happens? Electric resistant emergency heat comes on, essentially. When you have a better envelope, it basically means that the capacity of that equipment can meet load at lower temperatures. So a better envelope with the same equipment would allow us to stay in heat pump mode down to about 27, 28 degrees in this scenario. So a better insulated envelope actually allows a heat pump to operate effectively at lower outside air temperatures.
The problem with some of these little super high efficiency air conditioners, they're with larger coils and stuff, and they're taking a lot more sensible load than labor load, and they're just not taking more job.
Yeah.
And they find false ladies that sometimes that works down.
Yeah. Yeah, I mean, that's, again, it ain't the heat, it's the humidity dealing with that moisture load. And our climate zone is really the primary comfort factor because just about any equipment, most of the time, is going to be able to make cooling. Heating on the other side, heat pumps, this has always been one of the big, I guess, downsides to heat pumps is this balance point issue and when you have to run the backup electric resistance heat, how expensive is that to do? And it is nice that if you have a super insulated home and a super high SEER heat pump, you can get down to balance points that are pushing 0 at this point, but down at least into the teens. Yes?
Yeah, this comment about seeing the one-speed furnaces, because if you touch on duct design, because there's no such thing as well-installed flex duct. So they buy a bigger furnace with a bigger blower to overcome the friction air loss, and then that means the air moves faster over the coil, so it's kind of a self-defeating.
Yeah, I mean, basically, it's particularly true in heat pump systems, but it would be true on a furnace as well. Return side duct leakage is a killer in the heating season because, if I'm returning air from my house through that system, I'm bringing that return air and I'm trying to heat it up, right? So it's coming back into that system at what, 65, 67 degrees? And I'm trying to warm it up and supply it into the house. If that's outside of my thermal envelope and I have a return side duct leak and it's sucking in cold air in the winter, it's sucking in 40-degree air, that's going to kill the ability of my heat pump to do recovery. And then I guess to your point, you're saying, potentially they're going to upsize that furnace and end up basically, I don't see it as much happening with furnace systems. I see it largely with heat pump systems. That return side duct leakage just kills you in heating mode on a heat pump. And so, again, tight duct systems are required. If you went into an existing home today, probably the best 2 retrofits, I'm going to make 3 easy retrofits on the existing home. 1, go around with a hammer and smash all of the incandescent light bulbs, and then replace them with something else. I mean, literally, if you are still running incandescent light bulbs in your home, take a look at the technology. The price point of LED is way down. The efficiency of the technology is great. The color spectrums that are available are great. The technology is just market ready. I can pull up another presentation that I do where I just talk about this, and I went to the Home Depot and took pictures. And I've got 2 packs LED builder grade light bulbs for like $2.98. That's $1.50 a bulb. You can get them even cheaper than that. You can get a nice dimmable like Philips or Cree bulb for somewhere around $5. And then you can go get an Edison decorative LED that costs 10 or 15 or 20. You can spend a fortune, but you can go out and get a decent LED light bulb for somewhere between $1 and $1.50 a bulb. You can get a dimmable bulb, which you need if you have a dimmer switch, for $3 to $5 a bulb. It's the lowest hanging fruit. It's the fastest return on investment. Crunch the numbers, look at runtime, look at what you're paying. Trust me, the ROI is always going to work out. We can show return on investment of a couple of weeks for LED lighting retrofits in homes. So that's one. Air seal your ductwork. You could do this with a fancy product like AeroSeal that's sprayed into the ductwork, or you can do it the old-fashioned way. Get a bucket of mastic, get dirty, air seal your ductwork. Super fast return on investment, super cheap to do. It's just labor. It's really going to increase your comfort. It's going to increase the performance of the system. It's going to reduce your cost. And then the other one would be radiant barrier. If you have ductwork in a traditional vented attic, I would really think about putting up that retrofit radiant barrier. Those 3 things are really low cost. They're really simple to do from a, a DIY standpoint, and they are probably immediate low-hanging fruit opportunities to retrofit any existing home. How are we doing on time? About three? Okay, so I got a few more minutes.
Question.
Yes?
Concerning heating and air, how much of a play does the thermostat, how much of a job does the thermostat play?
Does a big job. I mean, aside from telling the system when we need to cool, which is really its primary function, the level of controllability really matters.
I guess I'm speaking of the NES.
Yeah.
Nest is good.
Yeah, so I'm kind of getting to answering that, which basically what I'm saying is, when are our HVAC systems the most efficient? When they're not running, when they're turned off, that's when they use the least energy. So, we actually had this conversation again on Wednesday with a building official for the city of Atlanta who was doing a renovation on her home, and she was like, wait, you're telling me I don't just want to keep my thermostat set to 70 all of the time? We said, no, you want to use setback. She said, but doesn't it cost more to try and cool the house back down after it drifts? And we're like, no, it doesn't. You don't want to maintain 70 degrees 24/7, 365 in your house, because your house doesn't need to be 70 degrees when you're not there, right? We're conditioning for human comfort. You can let the house drift up to 80 or 85 degrees and it's not going to hurt anything in the home. You can let the house drift down to 65, 60 degrees in the winter and it's not going to hurt anything inside the house. We are conditioning for human comfort. So saves energy. Now, programmable thermostats can be a pain in the butt. We had a loft in Kirkwood in Atlanta that I sold about 2 years ago. When I bought it, it had a basic non-programmable thermostat. I want heat, I want cold, I want this temperature or that temperature. I replaced it with a programmable thermostat, and my wife pitched a fit because she was like, I like the old thermostat. You told me what to do. When I leave, turn it off. When I come home, turn it on. I understood that. Now I don't know what this thing does. So even though I installed a programmable thermostat, we just ran it like a manual because my wife had learned, I turn it off when I leave. I turn it on when I come home. I can do that. And the programmable thermostat, I mean, aside from being more complicated, in the modern world, she and I don't work, 8 to 5:30 Monday through Friday. I'm here, it's a Saturday. She's working too. She's off on Wednesdays. I'm working from home on Tuesday, blah, blah, blah. Trying to set a schedule that says every single day the system should turn on now and turn off at this time becomes an operational nightmare. And then you're using override all the time and it's complicated. So programmable thermostats can save energy because they can put the house into setback when it should not be running. That said, new technologies like the Nest thermostat or wireless thermostats, we like one that's called, I forget the name of it, I'll come up with it in a minute, that you do everything basically from your phone, from an app on your phone. What's nice about these technologies is they're trying to simplify the process of programming a programmable thermostat, and they're basically smart operations. They're saying, I'm going to watch how you use your thermostat, and I'm going to adjust over time to match your usage patterns. I'm going to learn what you do, and then I'm going to make the decision for you based on how you use your home when I go into setback and when I come on and kick on the systems. So I think from that standpoint, that plus, oh, I forgot to turn my system off, let me go on my phone and turn it off right now, offers us some real opportunities.
Did you ever see, especially during the summertime, if you set your thermostat back, there's going to be less humidity, dehumidifying on the property. Your sheetrock is going to absorb a lot of that humidity, your furnishings, the rug. It's going to be more difficult for the system to dehumidify once it comes on.
That's really not true. And the reason is, again, the dehumidification happens where? At the coil, as the air passes over the coil and is dehumidified. So what we find is that when systems are left on all the time, they short cycle. And they don't actually dehumidify effectively because they go, I'm trying to keep it 70. Oh, it dropped to 60, or it's up to 71. System come on. 3 minutes of runtime. It's back to 70. System cut off. 20 minutes later. Oh, it's back to 71. System come on. 4 minutes of runtime. Cut off. They never reach the operating temperature on the coil where they're actually effectively dehumidifying. They never pull the air over the coil long enough, cycle and turn the air over in the home, and wring the moisture out of the air. Actually, drifting and then having more runtime as you recover back to temperature dehumidifies more effectively and provides greater comfort. I know it seems completely counterintuitive, but it's actually how the psychrometrics of the system works.
15 minutes to get the condensation to occur on the coil.
Yeah, and so if you're trying to recover and you're getting longer runtime on the system, it means you're turning the air over more in the house. You're pulling more air over the coil. You're running the system long enough for it to get to operating temperature where it dehumidifies, and you're actually going to dehumidify more effectively. And what? You're going to dehumidify when the person is in the house experiencing the comfort that comes with the dehumidification. So I know it seems a little counterintuitive, but you actually dehumidify more effectively when you come back from recovery from setback and you run the system and turn the air over the coil more.
6 or 7 hours to get back up during the system. An air conditioner is not oversized with 95 degrees.
Right, it's right sized that, you know.
It's oversized 80% down.
Yeah. Yes, it's right sized when it's 95 degrees, but it should also then run really long and dehumidify really effectively, right? Because the longer it's running.
If you set it back to 80 degrees, you want it to be 76, it's going to take 2 or 3 hours.
But his question was, yeah, about the dehumidification. It's going to dehumidify more effectively with that longer runtime. Yeah, absolutely. And people often kind of misconstrue, that's the other thing, like your air conditioner, well, if it's a variable stage equipment, then recovery happens differently. But in general, you know, it doesn't work any harder when you're trying to recover from setback. If it's fixed capacity equipment, it's on or off, and it uses the same amount of energy when it's on or off. It's just a question of runtime. And I'd rather have that runtime for 2 hours recovering with effective dehumidification when I'm home than have that runtime in 4-minute intervals throughout a 12-hour period when I'm not there. So, okay. Is everyone tired of talking about that?
Yeah.
Any questions? Yeah, because you're basically reducing, the house can gain heat and you're not calling for cooling. Yeah. All right, so ventilation. What is the purpose of ventilation? Primarily, it's to provide fresh air for occupants and dilute pollutants in the home. And that is why we ventilate homes. Historically, how do we ventilate houses? Windows, that's right. That, or we kept the windows closed and the houses were just really leaky. And so we got air changes, but they weren't necessarily good air changes. I'm breathing attic air, I'm breathing crawl space air, et cetera, et cetera. Fascinating to me, we open the windows in our house a lot. I mean, anytime that it's, you know, warmer than about 60 and cooler than about 85 outside, we turn off the system and open up the windows in our house. And that makes us unlike the vast majority of Americans. The vast majority of people who live in homes today never open the windows.
So you're not concerned about the humidity that comes into the house or pollen or anything like that?
Honestly, I am y'all probably, I use this phrase and someone, like a 25-year-old looked at me like they had no idea what I was talking about, but it's the cobbler's children have no shoes. Does that sound like a phrase y'all heard before? Don't say it to a millennial, though. They're like, a cobbler? What does pie have to do with it? They have no idea what you're talking about. You say the cobbler's children have no shoes. But, I mean, I live in a 1970s ranch with no insulation in the walls, no insulation in the roof, terribly air leaky, an old HVAC system. I need to completely redo my return and supply. I need to put a new roof on, I need to insulate above the roof deck, I need to put insulation in, I need to seal my basement. I've got a punch list 1,000 years long because it's my house. And so I'll get around to it when I get around to it. And so, you know, it just feels nice when it's 73 degrees outside, 75 degrees outside to open up the windows and let the air move. And we don't have allergies that bad, so, you know, we can dust the pollen or whatever. And it's, again, it's comfort. What's comfort to you? You know, I like the house breezy and open and air changes, and you know, if it's really polleny or really crappy outside, you know, maybe not so much, but, you know, except for the, you know, the blanket of pollen that we get sometime in, you know, late March.
Next year, when you get out, you'll change your mind.
We've been doing this for years, so I don't know. I mean, again, the cobbler's children have no shoes. I'm attacking the efficiency of my home from the operations side. Right? I've trained my wife to turn off the thermostat. Easy enough, right? So, anyway, the average American, though, most homeowners, they do not open the windows. They are relying on the house to ventilate, and unfortunately, you've probably all heard the house has to breathe, which is this idea that it needs air changes for indoor air quality and for drying potential and all this other stuff. And it's sort of like, well, we prefer that we not get our house wet to begin with, which would be one thing. And then really, the air changes that we want are for dilution of pollutants, which could include moisture, and for indoor air quality and human comfort. And controlled air changes are actually much better than uncontrolled air changes because you get to choose where the air comes from, you get to dehumidify and filter the air, you get to mix the air with the air that's already in the home, and you get to supply it to where the home, to where the air needs to go, and you get to choose when you ventilate. So controlled ventilation from a building science standpoint is much better than uncontrolled ventilation. And we always get these questions. Why get rid of leaks and then add ventilation, right? You know, it's the idea. Eliminate uncontrolled air changes and then reintroduce controlled, managed air changes. That's going to increase your comfort and improve your indoor air quality. Isn't ventilation an energy expense? Yes, it is. It costs money. For every cubic foot of air we bring into that house, a cubic foot of air goes out somewhere else, and that air we bring in has to be dehumidified, it has to be circulated, it has to be brought down to temperature. It costs us money to bring outside air into our buildings. But again, a leaky home has uncontrolled air changes, so you're paying that energy penalty on a leaky home regardless. At least on a mechanically ventilated tight home, you get to choose how much, where, and when that ventilation air comes into the home. So you can actually reduce the ventilation expense, though it does cost us money to bring outside air into houses.
Aren't there ERVs, these heat exchange systems that can clean the heat off the home?
Yep. I've got some slides coming up on that in just a minute. And there are new technologies, ERVs, HRVs. In our climate, we really want an energy recovery ventilator, not just a heat recovery ventilator, because it'll do some latent as well as sensible recovery, so it'll manage moisture a little bit. And the best products that we're seeing now are dehumidification ventilators. I'll show you some of those in a second. And then this question, is there only one way to do ventilation? And so ASHRAE 62 is the ventilation standard that our industry uses. And unfortunately, it says you can do negative pressure ventilation, positive pressure ventilation, or balanced ventilation like you would get from the ERV. And in our climate zone, we don't really like negative pressure ventilation strategies or exhaust-only ventilation strategies because they put that house back under an operating condition where it's negatively pressurized, and that exacerbates uncontrolled leakage, right? If we blow air out of a house, 50 CFM per minute, what has to happen? 50 CFM per minute has to come from somewhere. And so if our house is always under negative pressure, then we always are pulling in outside air from somewhere. And if we don't get to choose where that outside air source is, then we don't know whether it's attic air, crawl space air, you know, coming down our chimney air, who knows?
Yes.
Yeah. I mean, have you all seen this one? Somebody gets the big old giant hood range put in the kitchen, and now it blows like, you know, 1,200 CFM out of the house through their beautifully renovated kitchen. and then they call somebody out because they're like, my whole house smells like a chimney, what's going on here? You're like, oh, it's called makeup air, and your chimney is now provided. Any other questions? Yeah, we see this all the time, right? Somebody renovates the kitchen, they put in a giant blower door sized fan into their kitchen, and then they blow, 2,000 CFM of air out of their house, and they wonder why it smells like a chimney. Well, it's because you don't have a makeup air pathway, and you're putting your house under a ridiculous amount of negative pressure. And in fact, the IRC says, what? Exhausts over 400 CFM need to have what? Makeup air. Do you think that gets complied with all the time? On a renovation? Heck no. Again, what do? I put in hoods. Right? You want a big old Viking stainless steel range hood? I can do that. Put a hood in, no problem. Maybe that contractor knows about makeup air. Maybe they don't, It's the wild, wild west. All right, so ASHRAE 62 gives us some rules. It says kitchens, spot ventilation, minimum 100 CFM can be done continuously or intermittently. Baths, well, I guess intermittent. Spot ventilation, minimum of 50 cubic feet per minute. So these are spaces in homes that do need intermittent negative pressure ventilation, and at a minimum, per the ASHRAE 62 standard, kitchens need 100 CFM, baths need 50. Of course, kitchens get way more than this typically. And bath fans, seriously, how many of y'all have been out to a new home and seen a bath fan that's already installed in a way that the first thing it has to do is make a 90-degree or 180-degree turn with that exhaust duct, right? You think that thing actually pulls its rated CFM? Heck no. So, we always say if you want to get 50 CFM from a bath fan, put in at least an 80 CFM bath fan and install it, and then it might be in the 50 CFM range. So when someone puts in a 50 CFM bath fan and then they put it into a little 4-inch duct and they run it through, 17 loops before it goes and dumps into the attic. By the way, where should exhaust air always go? Outside of the freaking house. Yeah, come on, guys. Like, you see them terminating into the attic, and then we actually get comfort calls where people have exhausts that dump into their attic, and then they call us and they're like, we got really high humidity. It's like, yeah, it's because your shower exhaust dumps into your attic. You should probably go outside. Any other questions? It's crazy though, right? A lot of these things that go on in houses are really simple to fix, but people come in with blinders. Like, I do one thing. I put in, exhaust ventilation. So you've got a comfort problem. I'm going to put in a bigger fan. But if your exhaust is dumping into your attic, the bigger fan doesn't fix the humidity problem that the house is experiencing. So, ASHRAE 62, 2004, 2007, and 2010 had an equation that said how much whole house ventilation your house needs is 7.5 CFM per person. And you determine people by number of bedrooms plus 1. So how many people are in a 3-bedroom house? 4. How many people are in a 4-bedroom house? 5. Very simple. Number of bedrooms times 7.5. Why does that just say plus? Oh, plus. Sorry. I was like, shouldn't that say number of bedrooms plus 1? I was like, oh, no. It's 7.5 per person. Number of bedrooms plus 1. Plus 1 CFM for every 100 square feet of conditioned space. And the 2012 and the 2015 IRCs have a reference table written into them because they both say mechanical ventilation is required in all new homes. There's no more, if you test and if it's this tight, then you have to do ventilation penalty. No. 2012 and 2015 IRC say, IECC and IRC say you have to do ventilation in new homes. So we've eliminated that confusion about how tight is too tight, and then I have to do ventilation. And it just says they have to do ventilation, and it has a reference table, which is basically the ASHRAE equation. And you look up your number of bedrooms, and you look up your square footage, and it tells you how many CFM of ventilation area you need in your home. And it's really simple and straightforward. So that is a nice thing that is in the new cycles of the code. ASHRAE 62 2013 came out, and they changed the equation. The IRC and IECC have not updated to this newer version of ASHRAE. Their tables are based on this equation. The new version of ASHRAE says 7.5 CFM per person plus, 3 CFM per 100 square feet. triple what is in this standard. And I'll be honest, this was heavily debated. Have you all ever heard of a guy called Joe Stiebrick? Yeah, he's a famous engineer. Casey Jones, last famous engineer. Anyway, he's a famous engineer in the building science world, and he was involved with the ASHRAE committee and was like, this is too much ventilation, and wrote a separate standard that's actually somewhere between these two. So the debate rages in the building science world. We all know that controlled mechanical ventilation is a good thing, and that we use this saying, build it tight and ventilate it right. Everybody can agree that a tight house that's well ventilated gives you good control of energy, gives you good comfort, reduces risks around pollutants and contaminants and all these other things. The debate rages about how much ventilation is the right amount. So the new version of ASHRAE has significantly increased the amount of ventilation that we're going to see in homes, and particularly in our climate zone, some people say this might be too much. So the codes that the state of Georgia is looking at right now reference the older ASHRAE standard that was around for a long time and produces a lower ventilation rate based on 1 CFM for every 100 square feet of conditioned area. So just be aware that the new ASHRAE has pushed that number way up, and it's a big debate in our industry about whether or not that is too much ventilation air, particularly in a humid climate.
How is the ventilation air introduced?
Great question. There are a couple different strategies. And there's the equation, there's some stuff. But essentially, we see almost most commonly this strategy for introducing mechanical ventilation into the home. This is a rigid duct, 6-inch duct typically, runs to the outside, ducted to the return side plenum. It has a motorized damper, and it has a control, often called an air cycler, that determines basically how many minutes of the hour that damper is open. And what this system does is it looks at the air handler with this controller, and if you're in the middle of the summer and you're getting lots of runtime on your system, then it just watches the system and it says, okay, every 15 minutes or 20 minutes or 30 minutes, whatever you have the timer set for, of the hour, I'm going to open up this damper and I'm going to allow the system to pull return air from the house, but I'm basically introducing an outside air duct leak, and it's going to pull some of the air from the outside. It's going to come down here, it's going to be mixed with the return air, it's going to go over the filter, it's going to go through the blower, it's going to go over the coil, and it's going to be supplied into the house. And it's going to put the house under slightly positive operating pressure, and it's going to mix in fresh air, ventilation air, with the return air from the house. If you're in a shoulder season and you're not getting any runtime on the system, and you have this set for 15 minutes an hour, after 45 minutes go by, it's going to look at that air handler, and it's going to say you didn't run. It's going to click on the air handler, not the coil, not the outside unit, just the air handler. It's going to pull in outside air, and it's going to mix return air, and it's going to give you 15 minutes of air cycling, and then it's going to shut off. Pros and cons. Super cheap. This system costs a couple $100 to put in on a new home. Also pretty cheap to retrofit. It gets you controlled mechanical ventilation at very low upfront cost, and it makes use of the equipment you already have. That's the biggest pro. Biggest cons? Well, you're using a big old fan to move air around, so it has the highest operational expense for most of the systems that we look at. And the other con being, if you are not running the system, then you're going to open up and bring outside air in, and you're going to be basically mixing outside air with return air from the house. You're going to be mixing it and filtering it, but you're not going to be dehumidifying it or cooling it because you're in a shoulder season and the coil isn't running. So it has pros and cons, but a lot of builders use it because it's the cheapest system and because it piggybacks onto equipment that all homes already have.
So what you're saying is you set the thermostat to off, that feature is still going to operate.
Right. It's still going to cycle the air for however many minutes of the hour you
You
have
can
set.
have your own motherboard, little motherboard control up next to the air handlers.
Is there a typical time that you would expect that to run if the system was not running?
It is actually completely controllable and adjustable. That's one of the nice things about it, is the occupant can say more or less for the runtime. And so in order to size it, you do that Ashtray 62 calculation, and then basically the size of this duct determines your CFM per minute. And you basically say, how much runtime do I need to meet the Ashtray calculation?
The ones I'm seeing are Honeywell, it's got an off and an automatic. You have a little slide switch.
That's it?
Yeah, and I,
This is an April air controller. Honeywell makes a similar controller. The on-off controller is probably $5 cheaper. And so someone's doing that.
But the question I have is there an average time that it should run? Because I'm hearing from people it's running 35 and 40 minutes on an hour.
Again, you can do ventilation continuously or intermittently. If you do it continuously, then you take the Ashtray 62 calculation, you look at the capacity of whatever your outside air system is, which for a system like this is basically determined by the size of this duct and how long the damper is open, and you match the CFM, cubic feet per minute from Ashtray, and you can do it continuously or intermittently. And what happens is, if you do it intermittently, if you're only ventilating 30 minutes out of every hour, you have to double the size of the duct. So I think probably people are going with smaller ducts and longer run times. But if you go with the probably slightly more expensive controller, the occupant can actually, determine more or less for themselves and not have it set to a fixed run time. We hear this too a lot, especially in the multifamily world, and especially in the affordable housing multifamily world, that people don't want to run the air conditioning systems, but they hear the ventilation systems running and they get upset about it. How do we turn this off? This is costing me money. I do not recommend this system, and I particularly don't recommend what we see the biggest failure with is when they have a open closet in a multifamily situation, and they've just got a free return, and they don't have a fully ducted outside air vent, and they're just trying to dump outside air into that closet. We see a lot of problems with that. At a minimum, that outside air vent should be fully ducted.
Tell me, does this, on systems where you've got dual zone systems, or two HVACs or more, is this only on one? Because I've only seen this basically when there's applied to one of the two HVAC systems. Does it apply to both? Two-level house, is you're supplying air circulating only to one level?
Again, I would put it on both systems, but I think someone could make the case that they were going to take the primary system for the home and they were going to do all of the ventilation on that system, and it'd be hard to tell them that's wrong as long as they're meeting the volume CFM that's required. I would put it on both systems, but I think you have a hard time if someone can meet the required rate with just one system of telling them they're not meeting the requirement. Another question? Okay.
I do have a comment about, when I find ventilation problems, it's usually on multifamily. You're on a fourth floor, the fire marshal used to let you undercut the door, now you can't. You've got no makeup air.
Yeah.
So you've got a bathroom and a dryer, a small unit, and an unvented oven place, and as you say, no return plan to pull an air cycle into. But, I mean, that's where I can smell it. You know, over the front door that they've got a problem with that. So that there's no design, there's no mechanical design for makeup air in those that I've seen.
Yeah.
Except in a couple, most of the time.
And that is the typical makeup air strategy in an apartment situation is basically depressurize and give a door undercut and hope for the best. And it's not a particularly sophisticated strategy. Again, on the flip side, I've had some affordable housing developments that have dedicated outside air ventilation systems designed to serve the entire building. And they decouple ventilation air from space conditioning, and they provide continuous ventilation, controlled, dehumidified, centralized, continuous ventilation to all of the units. It can be done. Does it cost more? Sure. But hey, they're getting the tax credit for a reason, right? It's not to put more money in their pocket. It's to spend more on the design to produce a more comfortable, more efficient structure.
They do the whole too, right?
I prefer systems where they don't try and pressurize hallways and depressurize units and then use transfer grills or something, because you can't possibly balance that system. You have no way to know which unit is getting how much air.
Except for the
Yeah, or sometimes their own condition. All right, you all ready to move forward? All right, here's another one. This is the same type of system, but instead of coming off of the sidewall, they're just coming in off the roof. The big thing about this is this should not be drawing air, 4 inches off the shingle. If I'm going to bring in outside air into my house, do you think I want to breathe what's coming off of a baking shingle in the summer? Probably not. So this needs to extend several feet up above the roof deck so that we've got a mix of air coming into it. But we see them all the time coming up and drawing air, 4 inches off of that bacon roof shingle, and that is bad.
You go into the soffit.
Yeah, could run into the soffit, certainly. That's a good location for it. Lots of times we recommend to people they basically go out to a soffit or a porch overhang and draw outside air in from there. It's a good location. Okay, here's another one. Somebody brought up an ERV, an energy recovery ventilator. This is a piece of equipment that will blow air out of the house, will bring air into the house, and it will use basically a heat exchanger inside here to precondition the incoming airstream with the outgoing airstream. They say it's free preconditioning, but you're running a fan, so it's not completely free, but you're not running a coil. It's not going to bring air all the way down to the temperature you want it to be. It's not going to fully dehumidify either. It's just going to do a little bit of tempering the incoming airstream with the outgoing airstream. But it is an energy recovery ventilator because it's recovering energy from your exhaust stream and sinking it into your incoming stream to give you a little bit of tempering. This is not the cheapest one that we've seen. Panasonic is actually making a small unit that costs maybe $300 that'll do like 35 or 40 CFM that might do a small apartment. That's just the cost for the equipment. Someone's going to charge you something to install it, but it's really at a price point where you might be talking $500 or $600 on a small apartment to put in an ERV instead of trying to do that ducted system into the return, or God forbid, a system that just dumps into a closet. And the fully ducted system to a return might be $200 to $300. The small Panasonic ERV installed that cost about $300 off the internet installed might be $500 or $600. So I think it's a really cost competitive, much better piece of equipment, and it gives you balanced ventilation, so you're not positive or negative. You're balanced, CFM in, CFM out, and you're getting recovery of energy from the outgoing airstream. So Panasonic makes a little one. This is one that's actually ducted in to the duct system on the house. Internet price on this, about $475, retail about $675. What it costs to have installed, if you know what you're doing, you can put this thing in yourself. If you want, you can have somebody else install it. They're probably going to charge you in the ballpark of what the equipment costs to put it in. Rule of thumb, take that, double it. It's probably what it's going to cost you to have it installed. Pretty efficient, very quiet, reasonable, sensible recovery, very efficient, and will give you balanced whole house mechanical ventilation, for maybe $1,000. Here's another one, and I will say we had the manufacturer of one of these products come Tuesday, speak to our state codes council. They've gotten the prices down on these things more like the $500 price range, and these are the best option for our climate. They're a dehumidifier ventilator. So it's going to provide ventilation air. It's also going to dehumidify that incoming airstream. And what do we say? It ain't the heat, it's the humidity. The humidity is the comfort factor that we really care about. So, at the time that we put this together, these things were running maybe $1,000. They cut that price point way down. You're still going to have to pay to have it installed, but you might be able to do a dehumidification ventilator at home for maybe $1,200, $1,500. So The prices are down on these. They are going to provide great comfort, controlled air changes. I mean, I think that for our houses in this climate zone, this is the best possible strategy for ventilation. Dehumidified, balanced ventilation. Oh shoot. I knew it yesterday. I can't remember the brand off the top of my head. Sorry.
Like Panasonic.
Yeah, this one may be, there's a bunch of manufacturers. I forget who, I'm not going to be able to remember the name.
ERV or anything like that, it's called a
Dehumidification ventilator, yes.
Where did you use it?
It has a drain pan and a line just like your unit, and they typically then just run that to wherever the condensate drain line is for the HVAC unit. Good question. Where does the humidity go? That's magic.
Linear battery. That flare, is it looking at fresh air or is it looking at humidification?
It will actually, depending on how, I think these are typically ducted in with the duct system of the house, so they would probably pull some return and provide you some dehumidification of the inside air, but primarily they're trying to dehumidify the outside air. I feel like you can have both. You can have it standalone, where it was just dehumidifying outside air, but if you're pulling any return from the house, it would dehumidify that as well. I think they most often install these installed with using the return and supply of the home, so you would get some return from mixing and some dehumidification inside. But it's primarily dehumidifying the outside airstream for ventilation. But I think it would improve the overall humidity comfort in the home.
Boy,
Yeah.
do you remember the old heating systems that used to have the built-in dehumidifier? Isn't this basically a remake of the old system?
Yeah, that was a humidifier in the heating system. Yeah, which is, don't do that. Do not superheat your air so that you then have to rehumidify. Also, this is really interesting. I teach a lot in Alabama. There's a guy over there that I've done workshops with who's a contractor. So he's been, in this industry for 30 years, built every type of home, commercial building, all sorts of stuff, and maybe a dozen years ago really got into the home performance contracting world, and just the whole idea of like doing this stuff right. And we've been teaching some workshops, and he tells this really interesting story. He got a call from an elderly couple in an existing home, and they called him out because they said, we're getting high utility bills, and our utility bills are just ridiculously expensive. Can you help us? And he said, sure. So he went around and did a visual inspection, and what he found was they had one of those old humidifiers in line in the return side of the duct, and it had been pulled out, and they were basically, it had fallen out, from gravity over time, and they were pulling in attic air into their duct system. So he basically took that thing out, sealed it up, said, here you go, I think this is going to dramatically improve it for you. And he got a call a couple of weeks later from the couple, and they said, wow, this is so great, we want to thank you. Our utility bills are way down. We're saving a couple $100 a month or whatever. He said, so glad to hear. A few weeks later, they called him back up and they said, we missed the best part. We used to constantly run around having to dust every surface in the home because of all the attic air that was being pulled into the duct system and sprayed all over the house through the supply ducts. And they're like, all of a sudden, our house isn't so dusty. And so they had this benefit of energy savings, and this even bigger benefit of all of a sudden they're not coating their house in dust. So they called him back up and was like, we appreciate the energy savings. My wife really appreciates not having to run around and dust the house every single day. So, that's an anecdotal, you could have a bad return or problem causing that type of stuff, but those humidifiers, we really shouldn't be having a need to humidify the air in our home. If you have that, lots of times it's because you're getting too much really cold outside air in the heating season that's making that air in the house be super dry, and you're treating the symptom of leaky ducts with trying to add humidification back into the system.
Well, you're also introducing moisture into your HVAC system.
Terrible building science. Yeah, yeah. And then if you've got internally lined ducts, you've got a recipe for disgustingness. Yeah, we shouldn't put humidifiers on duct systems. All right, a couple details. Again, I touched on these earlier. If